So what we're going to do today is finish up the notes. There's just two little sections left. Any questions before we get started?
I'm good.
Is everybody good? Okay, so what we're going to talk about today is something called the Nernst equation, which allows us to calculate E for non-standard cells. Then the other thing we're going to talk about are electrolytic cells, which are cells that require energy to run instead of produce energy like voltaic cells. So for this first section, all the stuff we've been talking about before has dealt with standard conditions. So the solutions have all been 1 molar. That was the main thing that we looked at when we were talking about standard conditions. When you have a concentration, when the concentrations of the solutions are not both 1 molar, that can actually create cell potential, and that can help drive a reaction as well. So when you're trying to solve for E cell, if it's a non-standard condition, we use this equation here, like I said, which is called the Nernst equation. So this is your E cell for non-standard. This is your E cell for standard. So for that one, you would use the same chart that we've been using to figure that out for all the other E cells we've done. So that calculating that E cell is just like what we've done before. N is still our numbers of electrons like we did yesterday. And then Q is our reaction quotient like we used when we talked about equilibrium, and we'll look at how to do that. So we'll do one of these. Before we do that, here's a comparison so you can kind of see the difference between standard and non-standard. So in the one on the left, the big thing to notice here is that the concentrations of those solutions are the same. So that's what makes this standard conditions. For non-standard conditions, notice those concentrations are different, and that difference in concentration can also help drive that reaction. So notice this one over here is generating a little more voltage than the one on the left. When you're doing these, it would tell you that it's non-standard conditions, or you'll notice, because in the problem, they're going to give you concentrations of things, when in all those problems we've done before, they didn't provide the concentration. So that'll kind of clue you in that that particular question is a little bit different. Okay, so this is what these look like. So for this one, it says, figure out the cell potential for an electrochemical cell based on the following two half reactions. So they're giving you the half reactions, or they might give you the overall reaction, kind of like what they did in the last section. This one, you'll notice, is a little bit different because they gave you the molarities. So if they don't give you those molarities, you can assume it's standard condition, and you can assume that it's 1 molar. If they give them to you, then you know that you're going to have to use this other equation. So when we set this up, we're going to solve for E cell, and we need the standard E cell, which we're going to calculate in a minute, minus 0.0592 volts over N, which is our electrons, log Q. Okay, and the Q we're going to get from those concentrations because it is a non-standard situation. Okay, so when we do this, we are going to look at, let's start by looking at how many electrons are transferred. So that's one of the things that we're going to need here. So E cell, and we're going to kind of run out of room here, so I'm going to have to erase some stuff as we go here. That's what we're looking for. We need the standard E cell, which we're going to calculate. We need to know numbers of electrons, and we need to know what Q is. Okay, so I'm going to erase this for now so we have a little more room here. So they've given us the half reactions that are sort of balanced, but they haven't balanced out the electrons. So if you notice, there's 2 electrons on this side, there's 3 electrons over here. So this one, because it is, the electrons are on the right, this is my anode. And then over here, the electrons are on the left, that's my cathode. Okay, so that's the first thing I can label. So to get the overall reaction, which is what I need to be able to solve for Q, I have to look at these and multiply these by some number so that those electrons cancel out. So if you remember back when we did our balancing equations, this is going to have to be multiplied by 3. This one's going to have to be multiplied by 2. Okay, so then that means my total electrons that I'm going to cancel is going to be 6. So that answers that question there. Then I'm going to add those two together. So I'm going to do this in a little less steps than what I did before. So I have 3 copper plus 2 MnO4 minus, oh, there's another concentration that we're going to need in a second, plus 8 electrons. So I am taking these and I'm distributing those through. I'm just not showing all those steps because we don't have a ton of room here. So 8H plus, that goes to, again, taking that and distributing that through, 3Cu plus 2 MnO2 plus 2 times 2 is 4 H2O. Okay, so that's my overall balance equation. So the reason I need that balance equation, the overall balance equation for this one, is because I need this Q value. And the only way I can get a Q value is by taking products over reactants raised to the power of the coefficient. Okay, now in this case, some of these are not going to be included. So this is a liquid, this is a solid, and then this one is aqueous, so I'll need this one. This one, the H plus is aqueous, and the MnO4 is aqueous. This one is a solid. Okay, so when I set up my Q, it's going to be Cu plus 2 raised to the third power over, let's see here, MnO4 minus raised to the second, and then H plus raised to the eighth. Okay, so take a second and look at that because I know we just did a whole lot of stuff there. So we added these two equations together because, again, the only way to get a Q value is to have that complete balance equation, which is what we did down here. Before we could do that, we had to take care of the electrons and make sure those electrons canceled and balanced out. And then we added them all together. And then just like before, when you set up a K or a Q, pure solids, pure liquids are not included. The only thing that would be included would be aqueous solutions or gases. And in this case, we only have aqueous solutions. So that's where this Q came from. Okay, so then what I'm going to do over here is I'm going to build this all into the equation, but I'm going to set up the Q so you can kind of see what that is. So what I'm doing here is my copper plus 2 is 0.01 molar. So Q down here is going to be 0.010 to the third. So I just subbed in copper's molarity divided by MnO4 minus's molarity, which is 2. And then that gets squared because of how we had this set over here. H plus, concentration is 1 molar. And then I raise that to the eighth because that coefficient in that equation was eighth. Okay, so that's my Q value. And like I said, I'm just going to put all of this into one equation. Okay, so now that I have that, the other thing I need before I can move any further here is I need my E cell. So E cell is going to be cathode minus anode. So what I have to do is I have to look up those values. So if I look up the value for this half reaction, that's going to be 1.68. And then for the first half reaction, that's going to be 0.34. And again, those numbers are coming off that chart. So this particular question kind of puts all of this stuff together that we've done so far. So the E cell calculation, and again, this is standard E cell, those values come off the chart. The N value is electrons that were canceled. And again, to get that overall balance equation, we used our balancing redox skills that we had that first day. Okay, so cathode minus anode, 1.68 minus 0.34. So my E cell value is 1.34 volts. So then that goes over here. Okay, so after all that, now I have what I need to be able to do that equation to figure out my non-standard E cell. So I'm going to erase this. Then we're going to go back to that original equation. So E cell is my E standard, which I calculated as 1.34 volts, minus 0.0592, that's part of the equation, over moles of electrons, so 6 moles of electrons, log Q, which I'm just going to sub this whole thing in here, 0.010 to the third over 2 squared times 1 to the 8th. So all of that ends up being 1.34 minus a negative 0.065. So be careful because there is that subtraction in there. So make sure that you're multiplying all of this stuff and then taking that original number minus the answer to that. So that's where that came from. So my non-standard E cell is 1.41 volts. So for this one, I actually get a little more voltage when the concentrations of those substances are changed. Okay, any questions on that? That was a lot. There's a lot going on in that problem, but any questions or any of that stuff that you didn't follow?
Okay, so the 0.34 and the 1.68, that came from the chart in our notes.
Yes.
Where did the 0.010, the 2, and the 1 come from?
010. Okay, these numbers here. So those numbers came from the problem itself. So when they gave you the data for that problem, when they gave you those half reactions, they also had in there the concentrations of those ions in those half reactions. So if this had been one that was at standard conditions, they wouldn't have had that extra information in there. So I'm gonna use a different color here. So see how that has like a molarity associated with copper, molarity associated with that permanganate, and a molarity associated with the H+. Those values are given because those are not standard values. The standard value would be 1. If it was 1, you wouldn't need it. But because this is non-standard, those are the values that then get put into that Q equation.
Okay, thank you.
Other questions? Okay, so there's only one of those. There's only one example in there. So as you're working through homework and the practice problems that we're going to do tomorrow, make sure you send me messages or ask me questions, or if you have one that you want me to work out and record, let me know and I'm happy to do that. All right, the last thing we're going to look at is something called electrolysis. So this is a process that probably the most common process that they use this for that we would know would be plating of silverware or jewelry. So if you've ever bought a piece of jewelry that says it's like 24 gold plated, or you have silverware that's plated, especially like in cheap jewelry where they plate cheap jewelry, it'll kind of flake off. This is a process that they use to do this electrolysis process. So what it is it's a process that normally wouldn't occur on its own. So an electrical current drives that non-spontaneous reaction. So the electrons are drawn away from the anode and connected and move towards the cathode. So the electrons still go anode to cathode, but if you notice, the charges on the anode and the cathode are different. Okay, so the anode has, in this case, a positive charge, the cathode has a negative charge. Now, since we're not spending a ton of time on this, really the only thing that you're going to have to do from this is be able to do a calculation where you figure out how much of a substance or how much of a metal was actually plated out, and we'll do one of those in a second. And then just know some general differences. So the main difference again is that an electrolytic cell has to have an energy supply. So it has to have a current supply in order for it to go, because it's a non-spontaneous reaction. Okay, so then let's look at an example of how to do this. So what we're going to calculate with this is these cells are run for a certain number of minutes. So you hook this up, and then if you think about what happened in the voltaic cells where the metal was deposited on one of those electrodes, that's what's happening here, except where the metal is deposited on a lot of times is a piece of metal, like those metals that you're trying to plate, like jewelry or silverware, etc. So what you would want to find out was how many minutes do I have to run this in order to get a certain amount of grams of metal deposited onto that particular electrode. So this is the overall setup for this. So it's basically a stoichiometry problem, not really stoichiometry like we've done before, but you're basically running it through a bunch of conversions. So there's two ways that these could be presented. One is they could ask you how many grams of metal are deposited once it runs, or it could say if this many grams of metal is needed, how many minutes would it need to be run? So this stoichiometry could go in this direction, or it could go in the opposite direction. So you could see these both ways, and you'll have examples of those in your homework and on a practice that we do. So when you set this up, if we were going in this direction, it would tell you how many minutes. So you would start with minutes, you would go to seconds, then you would convert it to coulombs. Then you would convert coulombs to moles, knowing there's this Faraday's constant. There's 96,485 coulombs per 1 mole. Then you would change moles of metal to moles of electrons, depending on the charge. Then you would convert to grams using the molar mass. Okay, and this is going to be a lot easier once we go through one of these. Okay, so this is our example for this one. So it says gold can be plated out of a solution containing gold plus 3 according to the half reaction. So this is our gold that's being plated out. So they're going to tell you what the metal is. A lot of times they'll tell you what the charge is. If they don't tell you what the charge is, then you just use whatever the charge is off the periodic table. So like everything in group 1 becomes a +1, everything in group 2 becomes a +2. If it's a transition metal where they have multiple charges, they're going to tell you which version of that metal you're using. Okay, so this is the half reaction that they're giving us. So we're going to take gold plus 3 and change it to solid gold. So we want to know how many grams of gold is plated out by a 25-minute flow of 5.5 amps of current. Okay, so what we're going to do with that is we're going to start with our time. So we're going to take 25 minutes. And an amp, the conversion that we're using for amp is a coulomb per second. So you'll see how that fits in there in a second. So we're starting with 25 minutes. We're going to convert it to seconds because of this measurement over here. So there's 60 seconds in 1 minute. So minutes is gone. So now we want to get rid of seconds, and we're going to use this 5.5 amps, which is the same as 5.5 coulombs per second. So 5.5 coulombs per second. So now seconds is gone. Now we want to get rid of coulombs. We're going to use that Faraday's constant that we used yesterday. So 1 mole of electrons is 96,485 coulombs. So that gets rid of that. Then we're trying to plate solid gold in this case. So for every 1 mole of solid gold, there are 3 moles of electrons. And this conversion is always going to correspond to whatever the charge of that metal is. So in this case, gold is a +3. So 1 mole of gold has 3 moles of electrons. If it was, say, copper +2, 1 mole of copper would be 2 moles of electrons. So that number always corresponds to whatever the charge on that particular substance is. Then, once we have moles of gold, now we need to get to grams. So I'm just going to do a molar mass. So 1 mole of gold is 196.97 grams. And this is just molar mass from periodic table. And then you multiply across. So let's get rid of the rest of this, moles, moles, and we're left with grams. So you multiply across, so everything gets multiplied, and then divide top to bottom, if you remember the stoichiometry rules here. And then for this one, our final answer would be 5.6 grams of gold. So these will always follow the same process. You might have a step less or a step more depending on how long it's running. If it's running for hours, you have to change it to minutes first. But you always have to get the time into seconds, because this is going to be, and they have to tell you what the amps are. And then the amps is what we use to get rid of seconds, going to coulombs. Faraday's number is what gets us to moles of electrons. The charge gets us to moles of solid metal, and then the molar mass gets us to grams. So these look really confusing, but once you do a couple of them, they all follow that same process. If it was going in the opposite way, they would tell you how many grams, and then you would just work backwards to get to minutes. Any questions about that one? Okay. So then the last slide that we're going to look at today, this is just a summary of these cell types. So it just kind of gives you a summary of the difference between them. All the electrochemical cells, whether they are voltaic cells or electrolytic cells, They always do anox red cat. So oxidation happens at the anode, reduction happens at the cathode. If you have a voltaic cell, the anode is the source of electrons. The anode has a negative charge. The cathode has a positive charge. If it's an electrolytic cell, the electrons are drawn away from the anode because they're connected to a terminal of an external power source. And then the electrons are forced to the cathode because of that power source that's connected. So voltaic galvanic cells, this is a spontaneous reaction as long as E cell is positive. The electrolytic cells are non-spontaneous reactions that are driven by a power source. So that's the major difference between the two. And then, like I said, you're not going to have to answer a ton of questions about electrolytic cells. The main thing that I'll put on the assessment will be having to do those calculations that we just talked about. Okay, in your notes, there's one other page that has some stuff about batteries. That is not something that we have to cover. I left that in there. If you want to read that section of your textbook, if you're interested in that, you can. But batteries and corrosion will not be on the test. That stuff is not in the standards for what we have to cover. So because of time constraints, we're just going to end the notes there. So any questions, anything else you want to go over or talk about?
When's our test scheduled for?
So test for you guys is scheduled for, the 23rd. So tomorrow, I'll post somewhere, and I'll post it today for you if you want to start it today. But there's a practice sheet called GEK. So it looks at delta G, looks at E cell, and it looks at equilibrium. So I'll post that as practice with the answers. On Monday, you can work through the station review. I'll post the answers for that. Tuesday, we'll do a homework quiz on the second part. So it'll just be the new stuff. So I won't put the balancing redox equations. I won't put the voltaic cells like they were before. But you may have to do some E cell calculations for these newer calculations that we've been doing. So that would be on the homework quiz on the 21st, and we'll do a review first together. Thursday will be a practice test. I'll make a Kahoot for you so you can do that. And then Thursday will be the test, and we'll do a review first with that. So the next couple days are just going to be a lot of practice. So I'll go ahead and post all that stuff so that you have the answers to it. So you can work ahead if you want, or you can kind of ask questions as you get to those things. Any other questions for today?
Will we still have a SLU exam at the end of all this?
I'm not sure about that because the guy at SLU has told us that because those questions are considered secure, because those are questions they use on their exams, he said if we cannot give a secure exam, then we may be exempt from that. So that's probably good news for you guys, because there's not really a way for me to give a secure exam where those questions could not potentially get out. I'm not saying you guys would do that, but just in terms of knowing that that test was given in a situation where the questions would not be able to be distributed because they use those questions every year. So I'm going to talk to him one more time. So it's very possible that you won't have an exam at the end of the year. So we'll have this test over this chapter next week. And then if we don't go back to school, we are going to have to go back and pick up what we can of that other chapter. And it'll be modified heavily so that we can do it under these conditions. But there are some things in there that you'll want to make sure that you're familiar with, especially if you're going on and you're taking chemistry again. So as soon as I know from him for sure, I will let you guys know, but it's kind of looking like you're probably not going to have that type of exam. We may still do some kind of summative evaluation, but it won't be like the exam we took first semester.
And if we don't take it, or do we still get the credit and stuff?
Yes, you would still get the credit because SLU is being really, really good to work with because he's doing the same thing with his students. Like they're taking basically open note tests that are under time constraints. So he's kind of in the same situation that we are, where he's having to kind of modify what he's doing as well. He also, one other thing that he's doing is he's recording all his lectures. So if he gets, I don't think he had this particular chapter done, but when he does record it, he's making it available to us. So if we want to make it available to you guys, if I can get to those, I can post those. So if you want to listen to him do the notes, and just to get a different take on things and kind of see, what they're doing over there. I can post those as well if you would want to use that for another review. All right, any other questions? Okay, let me know if you have questions or if you need more example problems of things, or you want to see other questions worked out or homework questions worked out, and I'm happy to do that and post those. Next couple days, like I said, is going to be review. So I will post those things on Google Classroom so you have them. And then we will meet back here. If you don't have any questions before then, we'll meet back here on Tuesday to do a quiz review, go over some stuff, and then we'll take the homework quiz afterwards, and then we'll start getting ready for that test next week.